As we jump into probability, there are all sorts of definitions that we need to know in order to work with calculating these probabilities of certain events given certain scenarios. So what we're going to do here is just talk through some definitions and then see how calculations work out with this specific example. So we have here our 10 jelly beans. One's going to be blue, 2 are purple, 3 are green, 4 red. And from this set of 10, we're going to draw 1 jelly bean from, let's say we have this bag of jelly beans. So let's talk about how these definitions would apply to these different scenarios. So an experiment, it's this attempt to produce a random phenomenon. In this case, our experiment is this idea of drawing a jelly bean from the bag. Drawing 1 jelly bean. So that's our experiment here. We're taking 1 jelly bean out of a bag. This experiment could adjust on the wording of the problem. Say they want to know what would happen if we draw 3 jelly beans or 4 jelly beans. We can kind of change this number of trials is what it would be. In this case, our number of trials is just this 1 jelly bean. And with that, we want to know these possible outcomes that can occur. The outcomes that could occur here, we could either see blue, purple, green, or red. So those are our possible outcomes, but then each has a different probability assigned to it based on how many of that color are in the bag. An event is a collection of outcomes. So what we could look for is like the event of, if we are choosing 2 jelly beans, the event of a blue and red, or blue and then a purple jelly bean. So we can describe events by kind of collecting different possible outcomes. In this case, if we're drawing 1 jelly bean, it could be a possible event of, if we just choose a color, like the event of drawing 1 blue jelly bean. And then you could just play around with the different possible colors that could go in there. So, but then based on number of trials, we could adjust like matching colors, or we could say like if we draw 2 jelly beans, what's the probability they're both purple? So having 2 purple jelly beans would be our event. Sample space is all of the possible outcomes, which we listed up above there. With sample space, we use kind of special notation. We use these brackets here, and then we just list out the possible outcomes. So we could see blue, purple, green, and red. And then you just close with the brackets. So it's this set that we're listing out. We list the set using mathematical notation with the brackets, and then it's just a collection of possible outcomes. If you've taken some algebra classes, this notation is very similar to our domain in terms of listing what's possible for our inputs. Here's just possible outcomes. So, notation that we want to use. When calculating probabilities, it's kind of like function notation from algebra, where we would use like f of x in algebra. Similar here, we're using p to represent probability, and then we have our parentheses, and then inside, this is where it won't be like a numerical value like it would be with f of x. Here we list our event that we're looking for. So like for our event blue, we would maybe look for p of blue, or we could use p of b. You can kind of use different notations that whatever makes sense to you. In the numerator, we list out the number of outcomes in the event. So like how many blue jelly beans would we have out of, and then the total number of outcomes. So say we wanted to calculate this probability of a blue jelly bean. What we do is figure out how many are in the set, which we have 1 blue jelly bean out of, and then we have a total of 10 jelly beans. So we have in the numerator the number of outcomes that match that event that we're looking for, and then the denominator just all outcomes combined. So this would be a 0.1. In calculations of probability, we keep values in the decimal form throughout calculations, but then when we go to make a sentence, we like to state it in percentage, because that's how we just speak more often in percentages. So we could say the probability of drawing one blue jelly bean is 10%. So just change it to a percentage there. In terms of rounding rules, when calculating probabilities, go to 4 decimal places just to keep the most accuracy going there. A rule that has to be true for probabilities when you do these calculations is that it has to be between 0 and 1. And that rule there can be your best friend during exams. In case you calculate a probability and say it comes out to 1.3, that would be saying that there's a 130% chance of that event occurring, and that's not possible for us. We're going to be limited to our sample space, so we're not going to go beyond it, and we're not going to go outside of it. So when you get these probabilities out, it has to be between 0% and 100%. Inclusively, it can have the value of 0 and 1, but anything negative or anything above 1 isn't possible for us. So then with these next definitions, we want to think about what if we repeated the process? Like drawing one jelly bean, these probabilities pretty set in terms of how they're going to occur. But what if I increase the number of trials? What if I thought about drawing 10 jelly beans from the bag? And I wanted to look at different probabilities. We could look still at this probability of a blue jelly bean. So theoretical probability is what we expect to happen. So pretty much based on the construction of our bag, we would expect to get a blue jelly bean one time. I mean, if we draw 10 jelly beans, and we are going to throw in this wording of with replacement, that's going to be important here, and we'll come back to why that's important. Meaning that when I draw a jelly bean out, I'm putting it back. But in terms of the construction of the bag, what we assume is going to happen for these jelly beans is we should see blue 10% of the time, purple 20% of the time, green 30% of the time, and red 40% of the time, no matter how many trials that we do. So these probabilities are kind of attached to these colors. So theoretically, these are the values that we should see. So if I draw 10 jelly beans, I expect to see this probability of blue 10% of the time. Or I expect to draw one blue jelly bean out of those 10 jelly beans. However, this isn't always true. Like, if we take this to flipping a coin, if I say, what's the probability of flipping heads? We would say 50%. It's 50-50 between tails and heads. But if I tell you to flip a coin 10 times, does that guarantee that you're going to get exactly 50% heads? Are you going to see heads exactly 5 times? No. And you can even play around with that. Flip a coin 10 times, maybe you'll get 5, maybe you'll get 6, maybe you'll get 4, maybe you'll get 1 head. There is probability attached to the likelihood coming through in terms of like 4 through 6 is pretty expected. As you get further from those values, it's a little less likely in terms of the number of heads you're seeing. But this is the idea of empirical probability. If we actually ran the experiment, what will we see come through? So with this, to find empirical probability, we'd have to actually kind of simulate this experiment. We would need a simulation. And what I would do is say I got some jelly beans, put them in a bag, and I draw 10 jelly beans. And I get these 10 different colors out. The empirical probability is I could look for this probability of blue. And let's say I did this and I got the blue jelly bean twice with drawing these out of the bag. So my empirical probability would be what I actually saw with those 2 blue jelly beans out of the 10 trials. So with this, I would actually have a 20%, but that's my empirical probability. Now, something that happens is the number of trials matters. So the fact that I'm using 10 jelly beans for each of these affects the probabilities and the likelihood of getting something very different from what I expected. So you could imagine is, what if I change this number of trials, which for number of trials we often use the symbol n for sample size. What if I bump this up to 100? What if I chose 1,000 jelly beans? So that would be me sitting with a bag of jelly beans and picking out a color, writing down the color, then putting that jelly bean back, and doing that 1,000 times, writing down basically 1,000 colors. Now, with the setup of our bag, we have our theoretical probabilities. When we have small sample sizes, working with these in a simulation can be very different. Again, if we think about flipping a coin, say we bumped it down to you flip a coin 2 times. Sure, you might see 50-50 heads, but maybe you'll see 100% heads. Maybe you'll see 100% tails. By only flipping the coin 2 times, it's way more easier to see those extreme cases. But if you think about keeping, continue flipping the coin over and over and over again, if you collect the number of heads and tails you're seeing, that number is going to get closer and closer to 50% as you flip the coin more and more and more. And that's the law of large numbers, that as we increase our number of trials, the probabilities that we expect, those theoretical probabilities, should start coming through. So that when we do our simulation with a large number of trials and I go to find that probability of blue jelly beans, it should be very close to 10%. And my values wouldn't venture as far as, say, if I had only done 10. So this is the law of large numbers. The more you repeat a process, the more those theoretical probabilities come through. Independence is something we need to think about, especially in these cases where we are repeating trials. So say we go back to drawing 10 jelly beans. So we're drawing 10 jelly beans, and I threw in this wording of with replacement. What this guarantees that with replacement is it's bringing in independence. And why that is that if we imagine we had this bag of jelly beans, I draw a jelly bean, I see whether or not it's what color it is, and then I put it back. When I go to draw the second jelly bean, all of my probabilities are the same. In terms of the construction of the bag, if I take one jelly bean out but then put it back, that's still my bag of jelly beans right there. So I still have these 4 probabilities coming through. So that's independence. It's the idea that the result of one event does not change the probability of the next event. Where we wouldn't have independence is if I had said without replacement. If I didn't put the jelly bean back. So let's say we have our bag of jelly beans. I choose a jelly bean, and say it was purple. Then I would only have 1 purple jelly bean left. So then, say I took that purple jelly bean, ate it, it's gone, it's not going back into the bag, so that's the without replacement part. Now when I go to draw my second jelly bean, the bag has changed. Now I only have 9 jelly beans, and all of these probabilities changed, because I would have a different denominator coming through. For purple, I would have a different numerator. So with that, we need to be careful of if we have independence or not. Basically, as events go by, is the probability changing? Another definition is complements. It's when we look for not some event. So if we had some event A and we wanted just the probability of not that happening, the notation we use here is for complement, and it looks like a little exponent of C there. This notation just says the same thing as probability of not A. It's just special complement notation. And what we can do is look at 1 minus the probability of that event that we want to remove. What this is doing essentially is taking, 1 is the idea of 100%. So if we have everything, you could think of that as our sample space. If we have all possible outcomes, what would it look like if we just removed our event? So let's say we wanted to look at probability of, let's go with not purple. And you can write it out like this, but for short notation, what you would see is probability of, and then we could just use P for purple, and then we'd have a little complement symbol on there. So if we want the probability of not purple, what we would do is take our 100%. And I mean, essentially what we're saying here is if we want the probability of not purple, then we want the probability of getting blue, green, or red. So we just want to take out these 2 jelly beans and say what's the probability of choosing anything but those 2 jelly beans. So the probability of purple would be that 2 out of 10, which would be a 0.8. So there's a 80% chance of not purple. So we can use this rule. With this case, it wouldn't have been the worst thing to do that. Look at what is the probability of blue, green, or red, which you'd basically be adding up. We have 1 blue, 3 green, 4 red out of all 10 jelly beans, and that would give you the same solution. But say we had a lot more cases. Say we had every color in the rainbow of jelly beans and we just wanted to look at the probability of not purple. If we had like 1,000 colors, this addition step here that I did is a lot more difficult because you'd have a lot more cases. But if you know all you have is 2 purple jelly beans and then these 1,000 other jelly beans, all you have to do is think about removing that specific case from one, and it's a lot easier. All right, so let's try out some of these rules. We're also going to talk about some rules that are going to come up in the next videos. So same set of jelly beans, we're just going to look at some different probabilities with it. So probability of a green jelly bean. This is just looking for a probability of a single characteristic. We're just drawing a single jelly bean out. So with that, you just set up numerator, denominator. Numerator would be the number of green jelly beans out of our total number of jelly beans, which would be a 0.3. And what you'd want to do here is make a nice sentence at the end that there is a 30% chance of drawing a green jelly bean. So with probabilities and just in general in statistics, it's always a good idea to make a sentence at the end. That's part of this process because there's not a lot of math here. It's like plug into the calculator, get the number, but the interpretation is very important. Probability of a purple jelly bean would be that there's 2 purple out of the 10, so that'd be a 0.2. So we'd make a sentence, there's a 20% chance. What I'll do is after this video, I'll fill in these sentences so that you can see them in the completed notes, but we'll just kind of go through the math here. What is the probability of drawing a blue or red jelly bean? Now, this word or is going to be very important in our calculations. And when you see the word or, you want to think addition. And in the next video, we're going to go into a lot more detail with this. But in terms of statistics, or brings through addition because we're looking at one or the other or both. Meaning here, we want to bring through the probability of blue jelly beans, or also the red jelly beans, or also if we had anything that was mixed like both blue and red, which we don't have in this case. But saying blue or red, or basically using or as the connector word, it brings through a lot of cases, one or the other or both. So what we do here is we want to add the probabilities. So probability of blue or red. In terms of our calculation, you could think in the numerator, well, we want to bring through what does it mean to be blue or red? Well, there's 1 case of blue jelly beans, and then we want to also combine with the 4 red jelly beans out of the 10 cases. So this would have a 0.5. So this would have a 50% chance of occurring here. But if we go back to just the construction of our bag up here, it's kind of like that we are good with choosing 5 of these jelly beans, the blue or any of the 4 reds out of the 10. So that makes our calculation and just comes through as addition. With D, we have the case of and. So we're looking for purple and blue. Now we see the word and here. This is trying to say both at the same time. And what we're going to see, so there is a video that we'll go through of talking about and how it brings through multiplication. But basically we're going to see these two scenarios that work with and. This case is different than multiplication. We would not use multiplication here. Why that is this case that we're looking at is we're looking at a single jelly bean and we're trying to see it to have two characteristics at the same time. So this is a special case of and where we're looking at one thing with two, and we could start adding in more characteristics. So what we want to see here is just one jelly bean. There's my silly attempt at a jelly bean there, but we want to see it to have two colors, purple and blue, at the same time. So if we think about our bag of jelly beans, this isn't possible. There aren't any jelly beans that have two colors. They're all individually colored. So with this, looking for probability of purple and blue, there are no cases that fit those descriptions out of the 10. So this would have a 0% chance of occurring because those jelly beans don't exist. So when you get to the multiplication video and we're talking about and, that's going to be a case of a sequence of events, kind of looking at the case of what if we chose two jelly beans? What would be the probability of seeing purple and then blue? That sequence of events is where you use multiplication. But this is a way that we'll also see and come through, but it's the idea of having one thing with these two characteristics at the same time. So the calculation's a little different. You just have to think about how many fit that description of both things out of your total number of outcomes. And then, what is the probability of drawing a jelly bean that is not green? And this is what we talked about up above with the complement rule. So we'd want to look at probability of not green, which would be 1 minus the probability of green. So we take 1 minus that 3 out of 10. Which would be a 0.7. So there would be a 70% chance of that occurring. Sorry, this is repetitive. That's our complement rule again that we talked about up above. Was the probability is not purple? We did that as well. So these are our different rules. With the addition rule, you're going to get more of an explanation of that in the next video. And working with and, while this is a special case here, we'll also talk more about this multiplication rule that will come through when we see and. All right.